All right. Don't get too intimidated this section. This section is basically just the previous sections as well. Because again, we're going to be using our calculators and our computers to kind of make things a little easier for us. All right. So one thing that's going to make this section a little easier is if you remember 3.5, function transformations. Okay. There's a bunch of function transformations. And we can kind of combine them all by writing things in this form. If we have some a times f of bx plus c plus d. Remember, a whole bunch of things. Like this is just multiplication on the inside or the outside, addition on the inside or the outside, and negatives do things too, remember. Okay, so we would start with a horizontal shift and end with a vertical shift and do everything in the middle, if you remember the order in which I recommended doing things. So what this is saying, right, this is saying that we go c units to the left. Right, if we're adding c on the inside, that's c units to the left. And then d, we touch d last. A is on the outside. It's a vertical change. A vertical stretch or compress. Compress? I like that. Vertical stretch or compress. Depending on whether A is big or small. Remember that B was a horizontal multiplication on the inside. Horizontal compressing or stretching. Notice I'm writing this in a different order. Because if B is big, that's a compression. Where if A is big, that's a stretch. All right, so watch out for that. And the last thing was D, units up. So you don't, like, we're going to be using computers for graphing a lot of this stuff. But if you remember these transformations, and again, remembering what the negatives do as well, then it's going to make things a lot easier for you. Okay. So let us get into it with example 4. And example 4 says sketch. And again, include at least 2 points. And the asymptote, just like before. And answer with the domain, the range, and the asymptote. So again, basically just like we've been doing this whole section, just some slightly more complicated things. What is 2 times the log base 3 of x? So this is just our standard logarithmic function with a vertical stretch of 2. It should be stretched out a little vertically. So when I'm making my axes here, notice that I'm not letting x be very negative. Why do I not care about x being negative? The domain of this function is when the inside of the logarithm is positive. So the domain here, I already know. Let's write it down. I already know it. You already know it too. The inside has to be positive, but the inside is just x here. The domain is just 0 to infinity. The range of all logarithmic equations or logarithmic functions are the same. And the asymptote is always at the edge of the domain. We could actually graph the asymptote right now. Green is a bad choice for that asymptote. It's hard for me to see. And again, you could plug in some points and get some nice points here, or you could use a graph. But what are some of the nice points? Well, log base 3 of 1 is easy. Right, if x is equal to 1, we get 2 times log base 3 of 1. 3 raised to the 0th power equals 1. You could use properties from before or a calculator to help you find that this is going to be a nice point. The point 1 comma 0 is going to be a nice point. When x is 3, we're also going to have a nice point. Why? Why did I choose 3? Because that's an input that I know how to evaluate the log from. Log base 3 of 3 is 1. Multiply that by 2. The point 3 comma 2 is on the graph. Etc. But again, you don't have to do this. You don't have to make a table. You don't have to do it by hand. But it's good practice. We're going to be looking at y equals 2 times the log base 3 of x. What are some nice points on this graph? Some nice points that we can graph. 1 comma 0, just like we said. 3 comma 2, just like we said. 5, it kind of looks like a nice point, but it's not actually a nice point. It's close. 9 comma 4 is going to be another nice point. Okay, 1, 2, 3, 4, 5 is right here. 10 is right here. 9 comma 4 is also a nice point. Okay. And I like graphing these in a different color, actually. And then just connect it with that logarithmic shape. Like so. And that's how you do it. And remember, if this base were bigger, then it'd be much flatter. If this base were smaller, it'd grow more quickly. That's the effect of the base. Let's do part B. Wait, did I answer everything I wanted to? Included the points, included the asymptote, domain, range, asymptote. There we go. Let's do part B. Part B was saying g of x equals the common log 4x plus 16 plus 4. So there's a lot going on here. It's the common log. That's log base 10. It's going to be really flat. It's going to take forever to grow. There's a bunch of function transformations. This whole thing got moved up 4 units. Shifted to the left 16 units. And then horizontally compressed by 4. It's going to be a lot harder to do this by hand. Still possible. Finding those nice points is going to take a little bit of work. The short answer is you don't have to. Okay? So let's just go over here and graph it. Common log of 4x plus 16 plus 4. And this time, again, you can find nice points here, but you can also just plug in approximations. All right, so specifically, the asymptotes and the intercepts are easy ways to approach this problem. All right, so let's graph, let's make our axes. Here we are going to actually need negatives. So what are the nice points here? 0 and about 5.2. 1, 2, 3, 4, 5.2. And let's label it. Since they're not super nice, let's include this. 0 is about 5.204. And then our x-intercept was at -4, and this was a really nice point. So you don't have to label this one. It is what it looks like. And then I think it would be a good idea to also include one in the middle. Like -3 is about 4.6, 4.602 at -3. 4.6 is around here. Again, since it's not an exact point, let's label it. So before we connect these, it's way easier. Oh, wait. This point is not at -4. Why do I know that this intercept is not actually at -4, even though Desmos says it's at -4? What's going on here? What's the problem? How can this not be at -4? We'll erase it later. Let's find the domain, the range, and the asymptote. Okay. So the domain of a logarithmic function is when the inside is positive. The inside of the logarithm is 4x plus 16. Let's solve this for x. That's when 4x is bigger than -16, or x is bigger than -4. And remember, in this case, even though there's a negative, we don't have to switch the direction of the inequality. It's only when we multiply or divide by a negative. The negative being elsewhere doesn't matter. So our domain is -4 to positive infinity. Ah, so that's why the intercept can't be at -4. -4 is not in the domain. It's going to be really close to -4, though. Yeah. Okay. Range. Well, it's a logarithmic function. Every logarithm hits every y value. The range of all these log functions is all the same. And the asymptote, that's going to always be at the edge of the domain. X equals -4. So let's fix the graph a little bit. And this is why graphing things by hand is so useful. Oh, it's going to bother. All right. This is why graphing things by hand is such a useful skill to have. Because it shows that you understand what's happening. If we graph that at -4, it would show that we didn't understand what was happening. Right? Let's do our asymptote. We'll do it in blue. Asymptote is at -4. Goodness, I'm really bad at drawing straight lines. Like so. And then, yeah, this red point is just so close to -4, but it's not actually -4. If you actually if you really want to zoom in on this, it might give you a, no, it's really close to -4, but we know it can't ever hit -4. So when we plot it, let's plot it really close to -4, but let's not actually plot it on -4. And it's like -3.999999 something. And you could solve, okay? But it's not super necessary because remember, the instructions only told us to include at least 2 points. So we don't have to say what this third point is anyway. Just make sure it's really close to -4. And this is kind of the worst case scenario, which is why I wanted to include it in this video. You can do a problem like this. You can do a problem like anything, all right? And again, it's very flat. In fact, it's probably a little flatter than this. I'm not really going to be splitting hairs when I'm grading this. Okay. Just include the 2 points like we have right here. Have the right shape, have the asymptote. And that's what I'll want from you. But let me know if you have questions about my expectations. That's always a great question to ask me. Hey, Jason, is this kind of like what you were expecting? Is this, and something like that is a great question to ask. Or what were you really asking for in that question? Is another good question to ask. Okay, so good luck. Don't be a stranger. Bye-bye.